welcome back to the deep dive. You're here because you want to understand complex topics, really get into them, but without feeling totally swamped, right?
Exactly.
So today we're cracking open this really interesting idea. It's called optimal brain damage.
Sounds a bit dramatic, maybe.
It does. But stick with us. It's from a paper back in 1989, LeCun, Denker, and Sola, and it's basically a super smart way to make AI, specifically neural networks, more efficient.
Yeah, and you've probably heard all about these massive language models, right?
Yeah.
Hundreds of billions of parameters. They're everywhere.
It's huge.
But what we're digging into today is kind of the opposite idea. Sometimes making these AI brains, well, smaller and more focused is actually the way to go. And optimal brain damage was one of the first big ideas pointing that way.
Okay, so our mission for this deep dive,
Yeah.
understand this weird-sounding concept.
Hmm.
How can damaging an AI actually be good? What's the core thinking? And really importantly, how does this connect to the buzz around small language models today?
Good plan. Let's start with the flip side, maybe. Why aren't those giant models always the perfect answer?
Right. So they can do amazing things, no doubt. But the size itself, it creates problems, doesn't it?
Oh, absolutely. First off, just training them takes, well, a massive amount of computational power. Think about Google's Gemini Ultra reports. Said it costs something like $191 million just for the training.
Wow, that's mind-boggling.
It is. And it's not just a one-off cost either.
Yeah, I was going to ask about that. Every time you ask one of these things a question.
It's using energy. Quite a bit, actually.
Yeah.
There was research suggesting a single ChatGPT query might use like 10 times the energy of a simple Google search.
10 times. So there's a real environmental cost there, too.
Precisely. And then there's the performance aspect, specifically something called overfitting.
Okay, explain that a bit.
Sure. Imagine you teach a student only one very specific type of math problem. They get really good at that one problem. But give them something even slightly different, and they're lost. A huge network trained on, say, limited data can do the same. It sort of memorizes the training examples instead of learning the general rules underneath.
Ah, so it can't generalize well to new stuff.
Exactly. And the original OBD paper actually pointed this out, referencing earlier work. It's this constant trade-off. You want low error on your training data, but you also need the network to work on stuff it hasn't seen before. Just making the network bigger and bigger doesn't automatically solve that.
Okay, so the giants have downsides.
Yeah.
Cost, energy, potentially overfitting, which naturally leads us to this thinking small movement.
Right. There's a lot of excitement now about SLMs, small language models. These only have a few billion parameters, not hundreds of billions.
And big names are getting involved.
Yeah, companies like IBM, Google, Microsoft, OpenAI, they're all exploring this space. Quantum Magazine had a good piece on this recently.
So what are these smaller models good for? Are they just like less powerful versions?
Not exactly. They're often more targeted. Think about summarizing a meeting transcript right on your device, or a healthcare chatbot that knows a lot about one specific area, or even just collecting data from smart home devices efficiently.
Things that don't need to know everything.
Exactly. Zico Coulter at Carnegie Mellon made a good point. He said, for many tasks, an 8 billion parameter model is actually pretty good.
And the practical side seems huge, running on a laptop or your phone.
Yeah, without needing that constant connection to a giant data center. And of course, way less energy consumption.
It really makes you wonder if we've been building sledgehammers to crack nuts sometimes.
It's a fair question. And this idea, shrinking networks by removing parts, it's not new. It goes right back to that 1989 paper, Optimal Brain Damage. It really set the stage for what we now call pruning.
Pruning, like trimming a rose bush, getting rid of the dead wood.
That's a great analogy. You remove the unnecessary or less productive parts to make the whole thing stronger, more focused.
And didn't the Quanta article mention our own brains do something similar?
Yes. Synaptic pruning. As we age and learn, our brains actually get rid of some connections between neurons to become more efficient. It's kind of a natural optimization process.
Fascinating.
And Jan LeCun, back in that '89 paper, he made a pretty bold claim. He suggested you could maybe remove like up to 90% of the parameters in some networks without hurting performance.
90%, that's huge.
It's massive. And his optimal brain damage method, OBD, was the technique he proposed to figure out which 90% or however many you could safely remove.
Okay, let's get into that then. OBD, how does it work? What's the magic?
Well, the core idea is pretty straightforward. Find and delete the connections, the weights in the network that aren't really doing much important work.
Okay, And the goal is,
Several things, really. Better generalization is a big one, performing well on new data, but also potentially needing less training data to begin with and making the final model faster at learning and making predictions.
so how do you know which weights are unimportant? Is it just the ones with small values, like close to zero?
That's the simple approach, yeah. Magnitude-based pruning, just chop out the smallest weights,
Yeah.
and it kind of works.
But OBD is different.
Right. OBD's key insight was that just because a weight is small doesn't mean it's unimportant.
Right.
It introduced this concept of saliency.
Saliency, like how much it stands out?
Sort of.
Mhm.
It's more like how much does the network's error increase if you delete this specific weight? High saliency means deleting it will be bad. Low saliency means maybe it's okay to snip it.
Ah, okay. So it's about the impact of removing it, not just its current size.
Exactly. And to figure this out, OBD uses some calculus specifically, second derivative information. It comes from something called the Hessian matrix.
Uh-oh, math alert.
Haha. Yeah, don't worry too much about the details. But basically, the second derivative gives you a much better sense of how sensitive the network's error is to each specific weight. It's a more refined way to measure importance than just looking at the weight's value.
Like fine-tuning versus just a rough adjustment.
That's a good way to think about it. It lets you identify the weights that really aren't contributing much to the overall accuracy.
Okay, I think I get the concept. What's the actual process, like step by step?
Typically, it goes like this. First, you train your network as usual, get it working reasonably well.
Standard stuff.
Then, you calculate the second derivatives for all the connections. From that, you compute the saliency for each one. The paper gives a formula.
Okay.
Next, you rank all the connections by their saliency, lowest to highest. And then you just delete a certain number or percentage of the ones with the lowest saliency.
The snip.
Snip, snip. And often, after pruning, you'll retrain the network a little bit to let the remaining weights adjust. And you might even repeat the whole cycle, prune, retrain, prune again.
And the paper showed this worked better than just cutting the smallest weights. You mentioned a figure.
Yes, figure 1A in the paper. It's a graph comparing OBD to simple magnitude pruning. It clearly shows that for the same number of parameters removed, OBD causes a much smaller increase in the network's error. It's just smarter about which parameters to remove.
Makes sense. And they tried this on a real task, handwriting.
They did. Recognizing handwritten digits, like for zip codes, they had a network, trained it on thousands of examples, tested it on thousands more, and applied OBD. It was solid proof it worked in practice.
And wasn't there that really surprising result you mentioned, where they got rid of a whole layer?
Yeah, that was wild. They used OBD kind of like an analysis tool, looking at the saliency of big groups of parameters. And they noticed that, wow, this entire layer, the second to last one, seemed to have really low saliency overall.
They just deleted it.
They did. It cut the number of parameters basically in half. And the performance, well, the error on the training data went up a tiny bit, as you'd expect.
Right.
But the error on the test data, the unseen digits, barely changed. And in some runs, the test accuracy actually improved slightly.
It got better after removing half the brain.
Kind of. It suggested the original network was maybe overly complex, maybe overfitting a little, and making it smaller actually helped it generalize better. Less really was more.
Wow. Okay, that really brings it home. So how does this, nearly 35-year-old idea connect to today's small language models?
It's incredibly relevant. The core idea is pruning, focusing on efficiency, finding the truly important parts of a network. They're absolutely fundamental to building effective SLMs.
So people are still using pruning techniques inspired by OBD.
Definitely. As the Quanta article mentioned, pruning is a key tool for tailoring SLMs for specific jobs, or getting them to run efficiently on, say, a phone or a sensor. It's about optimization.
Even with newer techniques around, like I've heard of knowledge distillation.
Yeah, knowledge distillation is another important technique where you use a big, powerful model to generate really good training data for a smaller one. That's super useful. But pruning is often complementary. You might train a small model using distillation and then prune it further to make it even leaner and faster for a specific deployment. And researchers like these smaller models too.
Why is that?
Well, as Lisham Choshan from MIT IBM pointed out, they're just cheaper and easier to experiment with, less compute needed. And because they're simpler, with fewer parameters, there's maybe a better chance of understanding how they're actually reasoning, making them a bit more transparent.
Lower stakes experimentation, potentially more insight. Makes sense.
Exactly.
Okay, so let's try and wrap this up. The big takeaway seems to be, it sounds weird, but strategically reducing the complexity of these AI brains, using methods like optimal brain damage or modern pruning. It can make them more efficient, more targeted, and sometimes maybe even better.
That's a perfect summary. It's this counterintuitive idea that less can be more. That foundational work on OBD really highlighted the importance of efficiency and showed that just scaling up isn't always the best strategy. It paved the way for the SLMs we're seeing emerge now.
It really makes you think, doesn't it? Our own brains prune connections to get more efficient as we learn. So, maybe a final thought for everyone listening. What other complexities in our own work, or maybe even our lives, are just unnecessary baggage? Where could we strategically prune to be more effective, more focused?
That's a great question. The trade-off between size and complexity versus real effectiveness,
Yeah,
it applies way beyond neural networks.
definitely something to chew on. Thanks for exploring that deep dive with us.